Welcome students to the MOOCs lecture on statistical inference. This is lecture number 16. In the last lecture, we have discussed an important property, namely sufficiency for estimating a parameter theta, and the condition was that a statistic T of x 1, x 2, x n, where x 1, x 2, x n is the sample values, is said to be sufficient for estimating theta if the conditional distribution of x 1, x 2, x n given t is equal to t is independent of theta. So, let me first give you some more examples of sufficient statistics. Example, consider normal mu 1. We need to estimate mu. Note that the variance is already known. In this case, it is 1. In general, the theory will work when sigma square is known. We have considered it 1. To keep it simple. Okay. So, L mu x 1, x 2, x n, that is joint density of x 1, x 2, x n under the parameter mu is equal to 1 over root over 2 pi whole to the power n e to the power minus half into sigma x I minus mu whole square I is equal to 1 to n. This is obvious because the likelihood function here is the product of the individual density, and we know that if x is normal mu 1, then the density of x is 1 over root over 2 pi e to the power minus half x minus mu whole square. Now, I am adding it because x 1, x 2, x n there are n observations. So, the L becomes the product of their individual densities, therefore, in the exponent they are being added, is equal to 1 over root over 2 pi to the power n e to the power minus half sigma I is equal to 1 to n x I minus x bar plus x bar minus mu whole square. So, what we have done? I have subtracted and added x bar. So, this allows us to write it as e to the power minus half sigma xi minus x bar whole square into e to the power minus half n times x bar minus mu whole square. This is because this term is constant, it does not depend upon I. Therefore, as I is equal to 1 to n, the summation gives me n times x bar minus mu whole square, and the product term will become 0 because sigma xi minus x bar will become 0. Claim x bar is sufficient for mu. So, what we are claiming that the sample mean is sufficient for mu. So, what we have to show? We have to show that joint density of x1, x2, xn given x bar is equal to mu is independent of mu. Since x1, x2, xn are normal with mean mu and variance 1, x1 plus x2 plus xn is distributed as normal with n mu and variance is equal to n. Therefore, x bar is equal to x1 plus x2 plus xn by n is distributed as normal with mean mu and variance 1 by n. Now, f theta of x1, x2, xn given x bar is equal x bar at k is equal to f theta of x1, x2, xn and divided by f x bar at k if x1, x2, xn are such that sigma xi upon n is equal to k or it is 0 otherwise. That is, if x1, x2, xn are such that x bar is not equal to k, then this becomes 0. Otherwise, it is the joint density of x1, x2, xn and of course, divided by the density of x bar at k is equal to 1 over root over 2 pi whole to the power n e to the power minus half into sigma xi minus x bar whole square into e to the power minus n into x bar minus mu whole square. This we have already seen, divided by, since x bar is normal with mean mu and variance is equal to 1 by n, this we can write it as 1 over root over 2 pi into 1 upon root n e to the power minus half into k minus mu whole square divided by 1 upon n, and this is x bar is equal to k. Therefore, this is nothing but 1 over root over 2 pi whole to the power n e to the power minus half sigma xi minus x bar whole square into e to the power minus n k minus mu whole square divided by root n upon root over 2 pi e to the power minus half into n k minus mu whole square. So, now you can see that this cancels with this, and whatever remains, this is independent of mu, as the term mu does not occur here. Therefore, what we can say that x bar is sufficient for estimating mu. Consider again normal population such that x1, x2, xn are from normal 0, sigma square. Here again the mean is fixed. I have kept it at 0 to keep the equation simple. It works with whenever mu is known. We have to find out sufficient statistics for sigma square. Now, f of x1 is xn is equal to 1 over root over 2 pi sigma whole to the power n e to the power minus sigma xi square upon 2 sigma square. This is straightforward because again I am multiplying the individual density, therefore, it is coming out summation as the exponent. So, it is coming as summation of e to the power minus sigma xi square upon 2 sigma square. Claim sigma xi square is sufficient for sigma square. Therefore, we have to show that the joint density of x1, x2, xn given sigma xi square is equal to k is independent of sigma square. Then only we can show that sigma xi square is sufficient for sigma square. Question: what is the distribution of sigma xi square? We know xi is normal with 0 sigma square. Therefore, xi upon sigma is normal with 0 1. Therefore, sigma xi square upon sigma square is distributed as chi square with n degrees of freedom. So, let z is equal to sigma xi square upon sigma square, which is distributed as chi-square with n degrees of freedom. We need to find the distribution of sigma square z. So, if x is chi-square with n, what is the distribution of y is equal to Cx? We know that this is equal to f at x multiplied by dx dy mod expressed in terms of y. So, this we have seen when we are working on functions of random variables. So, this is equal to, we know that chi-square with n degrees of freedom at x has PDF is equal to half to the power n by 2 upon gamma n by 2 e to the power minus half x, x to the power n by 2 minus 1. Therefore, PDF of y is equal to Cx is half to the power n by 2 gamma n by 2 e to the power minus half y by c to the power n by 2 minus 1 dx dy, and since y is equal to Cx, dx dy is equal to 1 by c. Therefore, this is equal to half to the power n by 2 upon gamma n by 2 e to the power minus half y by c y to the power n by 2 minus 1 upon c to the power n by 2, because this is 1 by c. So, this c and that c together we have c to the power n by 2. Therefore, if z is equal to sigma xi square upon sigma square is distributed as chi-square with n degrees of freedom, then distribution of sigma xi square is equal to sigma square z is equal to half to the power n by 2 gamma n by 2 e to the power minus half y upon sigma square y to the power n by 2 minus 1 upon sigma square to the power n by 2 is equal to half to the power n by 2 upon gamma n by 2 e to the power minus y 2 sigma square y to the power n by 2 minus 1 upon sigma square sigma to the power n, where y is equal to sigma xi square. Therefore, f of x1 x2 xn given sigma xi square is equal to k is equal to 1 upon root over 2 pi sigma whole to the power n e to the power minus half to sigma square sigma xi square is equal to k divided by half to the power n by 2 gamma n by 2 e to the power minus sigma xi square upon 2 sigma square xi square to the power n by 2 minus 1 upon sigma to the power n if x1, x2, xn are such that sigma xi square is equal to k and 0 otherwise. Now, let us look at this. This sigma to the power n cancels this sigma to the power n and e to the power sigma xi square upon 2 sigma square, that also gets cancelled. So, we can see that after cancellation there is any term involving sigma. Therefore, what can we say? We can say that the distribution of x1, x2, xn given sigma xi square is independent of sigma square, and therefore, sigma xi square is sufficient for estimating sigma square. Sometimes it is not easy to calculate the conditional distribution of x1, x2, xn given t, because we need to know the distribution of t. For example, x1, x2, xn are from lambda x to the power lambda minus 1, 0 less than x less than 1. Is it a density? Integration 0 to 1 lambda x to the power lambda minus 1 dx is equal to lambda x upon x to the power lambda upon lambda 1 0 is equal to 1. Therefore, this is a valid PDF. Question is, what is sufficient to estimate lambda? L of x1, x2, xn lambda is equal to lambda power n into product of xi to the power lambda minus 1. So, from here we can see that the joint density of x1, x2, xn depends upon only the product of xi. So, it appears that to estimate lambda, only product of xi is important. We do not need any other information. Just like that, in Bernoulli we have observed that the joint density has been a function of sigma xi, and therefore, we could guess that sigma xi could be sufficient for P. Similarly, in case of normal with 0 sigma square, we could guess that sigma xi square will be sufficient to estimate sigma square. So, we can guess that product of xi should be sufficient. But we cannot easily find the distribution of product of xi. So, we need something else to establish sufficiency, and that something else comes from Neyman factorization. What he says that if x1, x2, xn are coming from a distribution with parameter theta, then a statistic T x1, x2, xn is said to be sufficient to estimate theta if the joint distribution if theta of x1, x2, xn or can be expressed as a product of two terms g theta of t multiplied by h of x1, x2, xn. Or in other words, let us look at these two terms. The joint distribution can be written as a product of two terms. The first term is involving the statistic t, and also it is involving the parameter theta. The product term h of x1, x2, xn is a function of the sample values, but it does not involve theta. Therefore, what it is saying, that is the factor that involves theta also involves the sample values through the value of the statistics t, and the other factor is independent of theta. Proof: I am proving it for a discrete case. For a continuous case, it can be proved analogously, but since it involves the function t and therefore it needs Jacobian, that makes it little bit more complicated, but the conceptually it is the same. So, the theorem is if and only if. So, we will have to show both the parts. So, necessity. Let t be sufficient for theta. Therefore, probability x 1 is equal to x 1 up to x n is equal to x n given t is equal to t is independent of theta. That is, probability x 1 is equal to x 1 up to x n is equal to x n given t is equal to t can be written at the most as a function of x 1, x 2, x n. That is no theta. Therefore, let probability x 1 is equal to x 1 up to x n is equal to x n given t is equal to t is equal to say h of x 1, x 2, x n. Now, the left hand side upon probability t is equal to t when as before x 1, x 2, x n are such that t x 1, x 2, x n is equal to t and it is equal to 0 otherwise. So, we can ignore this part. Therefore, probability x 1 is equal to x 1, x n is equal to x n is equal to probability t is equal to t into h of x 1, x 2, x n. Let us call it g theta of t, because this probability will automatically involve the parameter theta. Therefore, we can write the joint distribution as product of two terms g theta t involving t and theta and h of x 1, x 2, x n that does not involve theta. Conversely, suppose the above condition holds, that is P theta of x1 x2 xn is equal to g theta of t into h x1 x2 xn. Therefore, probability theta of t is equal to say t is equal to summation over all those x1 x2 xn such that t x1 x2 xn is equal to t of p theta of x1 x2 xn, that is all those values of x1 x2 xn that generates the value of the statistics t x1 x2 xn to be t. I have to sum them up to find the probability that the statistic t is equal to small t is equal to sigma over x1 x2 xn such that t is equal to t g theta of t into h of x1 x2 xn is equal to g theta of t sigma x1 x2 xn such that t x1 x2 xn is equal to t h of x1 x2 xn. Therefore, the conditional density p theta of x1 x2 xn given t is equal to t is equal to g theta t h of x1 x2 xn divided by g theta of t sigma h of x1 x2 xn such that x1 x2 xn are such that t x1 x2 xn is equal to t from here, otherwise it is 0. That is when t of x1 x2 xn is equal to t. Now, if I look at this, this is surely independent of theta, and if I look at this, this cancels out. Therefore, the term remains is completely independent of theta. Therefore, it satisfies that the conditional density of x1 x2 xn given t is equal to small t is independent of theta. Therefore, that is a necessary and sufficient condition to check if the given t is a sufficient statistic to estimate theta. When you look at the joint density, if we look at the term involving x1, x2, xn, in which form it is associated with the joint density, that gives us a clue of how to obtain a sufficient statistic. For example, binomial with MP, and suppose x1, x2, xn are n samples. We want to estimate P, then the joint density of L x1, x2, xn is equal to MC x1 p to the power x1 1 minus p to the power m minus x1 into up to MC xn p to the power xn 1 minus p whole to the power m minus xn is equal to product of m c x I is equal to 1 to n p to the power sigma xi 1 minus p to the power mn minus sigma xi. Therefore, if we look at the joint density of x1, x2, xn, we find that the sampled value are involved here in the form of sigma xi. What does it say? It says that sigma xi is good enough for us to estimate p. Therefore, sigma xi is sufficient for p. Similarly, let us consider beta 1 alpha beta, where alpha is known. Therefore, f of x1, x2, xn 0 less than xi less than 1 is equal to product of gamma alpha plus beta upon gamma alpha gamma beta xi to the power alpha minus 1 minus xi to the power beta minus 1. Therefore, we can see that the only term that involves beta is equal to product of 1 minus xi. Therefore, we can say that this is sufficient to estimate beta. Still, sometimes it is not easy to visualize the sufficient statistic. For example, x1, x2, xn are from uniform 0 theta, that is f theta of xi is equal to 1 by theta 0 less than equal to xi less than equal to theta 0 otherwise. What is sufficient for theta? Suppose I ask you the question. Now, 0 to theta, this theta is unknown to us. Now, I have taken n samples from here. What we can say that this is the highest order statistic. Only thing that we can say is theta is greater than equal to this value. And since theta is greater than equal to this value, we know none of these observations have any influence on that decision making. Or in other words, the best estimate that we can do for theta is through the nth order statistic or xn. Therefore, we can say that xn is the sufficient statistic to estimate theta. How to do it mathematically? Let us define a function kappa of a b which is 1 if a less than b and 0 if a is greater than equal to b. Therefore, f theta of xi is equal to kappa of 0 comma xi times kappa of xi comma theta divided by theta, and it will be 1 only if xi is greater than 0 or greater than equal to 0 and less than theta. So, only in these cases when a less than b, kappa is 1. So, when 0 is less than xi and xi is less than theta, then this will be 1, and therefore, this is going to be f theta of xi for each xi. Therefore, L theta of x1, x2, xn is equal to product of I is equal to 1 to n kappa 0 of xi kappa xi of theta upon theta to the power n. Or in other words, this is saying that the joint density function is a product of these terms. Now, kappa 0 xi is equal to 1 for all xi implies 0 is less than minimum of all xi, and kappa xi comma theta is equal to 1 implies for all xi implies xi is less than theta for all xi. Therefore, L theta of x1, x2, xn can be written as kappa of max of xi theta upon theta to the power n multiplied by kappa of minimum of xi 0 minimum of xi. Therefore, the term that involves theta is maximum over xi. So, for this suggests that xn is sufficient for theta. Okay, students, with that I stop here today. So, over the last 3 lectures, we have studied different properties of the estimators, namely unbiasedness, consistency, efficiency, and today we have seen examples of sufficient statistic. In the next class, I shall be dealing with how do we actually estimate a parameter from the observations x1, x2, xn, or in other words methods of estimation. Thank you so much.